All right, so what's going on, y'all? This one's also a little bit longer, but you should be able to understand everything. I go into detail. There's a lot of tricks, I guess, you could kind of learn, but I mean, you'll be all right. It says, for the plain truss structure, determine the displacement of node 2 using the stiffness method. We also have to determine the stress in element 1. They give us area, the modulus of elasticity, and the length. Not the length of the bar, the length of the I guess the horizontal axis right there, whatever you want to call it. But point is, we got to determine the stress and the displacement at node 2. So let's go ahead and get started. All right, so just like problem 319, right? Yeah, the one we did previously. This is the stiffness matrix we use, right? It's EA over L. This is only for 2D problems. The C here is cosine, the S is sine, and it's symmetrical. So yeah, it's pretty straightforward, right? So before we get started, they give us a length of 100 inches, but that length is this length right here. So this right here is 100 inches. And we want this length right here. Let's label it X, okay? Let's go this way, just like that. And it's pretty easy to do, right? So we know the angle's 45, so it's cosine. We use cosine because we know this value, right? Cosine of 45 degrees is let's put this as step 1. Cosine of 45 is equal to adjacent, which is 100, over hypotenuse, which is what we're looking for. If you do the math, you will get X is equal to 141.42 inches. So we're gonna need this number, right? Obviously, it's the length of the bar. So don't get this confused. This is not the number you use for EAL. That's just giving this measurement right there. But now that we have that, we could go ahead and start doing the table, right? So again, we do this table because it helps us see things easier. So let's put element. In this case, we have 2 elements, right? 2 bars, 1, 2. Let's go ahead and do the table like this. Let's go push it all the way out, because we're gonna need some space. All right, so it's element. Then after we identify the element, it's gonna be element 1 for the first one, right? Let's do the first one here. That theta. Wow, this bar is a little crooked. I know it's bothering me. So let's go ahead and fix it. There we go. Hopefully that's better. We'll see right now. But yeah, it's just bothering me. There we go. That looks better. So that's the theta, right? We find the theta of the bar. That's going to be 45 degrees. We're going to find the cosine of that angle. Again, because we want these values, c squared, s squared, cs. So cosine of 45 is radical 2 over 2. Sine of that angle is radical 2 over 2. And then next one is c squared. So cosine squared, that's half, right? Radical 2 times radical 2 over 4. You know what I mean, right? Square this. Same for sine squared. It's the same number, so same value, half. And then CS. So CS is cosine times sine, which is the same thing, right? So half. And it's only for the first element, okay? The angle's 45 because we would take it with respect to the positive x-axis. It's going this way, right? So it's 45 degrees. And one more, let's do EA over L. EA over L, if you do that right, it's 10 times 10 to the 6, because there's 1, right? So that's 10 to the 7 divided by 141.42. Your number is going to be 70,170. And let me go ahead and put this in pound per inch. Okay, it's in pound per inch. So cool, we got that one. We do the same for every element. In this case, we only have 2, okay? So there we go, make it look nice, be neat. But sometimes you'll have different values for E for each bar, or things like that, just FYI. So it's always better to do it in table form. Let's go ahead and continue this angle now. It's from the positive x-axis, so that angle is 135, okay? It's this angle right here, 135. So got 135 degrees, and then take the cosine of that, you will get negative radical 2 over 2. Sine will be positive radical 2 over 2. Then square cosine, you will get half, right? Square sine, you will get another half. Cosine times sine, you'll get negative half. And same value, right, for L. It's the same distance, so nothing's changed, same properties, same length, same everything. So it's 70, 170. And again, that's in pound per inch. Now notice here they give us kips, so this number is actually 10,000 pounds because we want to be consistent, right? Pounds, inches, no feet, no, in this case just PSI, so that was good. This was inch squared. Just be on the lookout, okay? Make sure you have everything converted, you'll be all right. So yeah, we got the table, so that means we could go ahead and start to assemble the little matrices. In this case, we're gonna have 2 little matrices, one for this one and one for that one. So let's do K1, right? K of element 1 is equal to EA over L. So check it out. I'm gonna write EA over L. In this case, they both equal the same thing, right? 70, 170. But just for now, just keep it that way. All right. This element, this bar, is between nodes 1 and 2. So you're gonna have the X and Y coordinates of node 1, which is U1, V1, and then U2, V2. X and Y for each node. Same thing up here. You have U1, V1, U2, and V2. All right, cool. So we start filling this in, right? This is a stiffness matrix. So cosine squared, sine squared, cosine squared, sine squared. So it's half, 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 half. So it goes, what? Check out what I'm gonna do. Everything is half, right? The C squared is half, S squared is half, CS is half. I'm gonna factor out that 2. So it goes under, okay? Because it's half. So I'm gonna factor it out and everything just becomes 1. So it's gonna be 1, 1, 1, 1. CS, they're all positive here, so meaning the signs are gonna be the same here. So it's 1, negative 1, negative 1, 1, negative 1, negative 1, negative 1, negative 1, negative 1, negative 1, and positive 1. Cool. And it's symmetrical, right? So this one goes here, this negative 1 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 goes here, and this positive 1 goes here. There we go. All right, so that's the matrix for the first one. It's EA over L times half, right? And for the second one, it's gonna be the same thing. So I'm gonna do the same thing, right? It's EA over L, but again, C squared, S squared, and CS, they have half. So I'm just gonna factor out that 2 again, but the sign is different for CS, so we gotta be careful. It's not the same matrix. Okay, so we got, this one is between nodes 2 and 3. And I forgot how you determine, I think it was arrows, something like this. So if you go this way from 1 to 2, now you're going from 2 to 3. Maybe somebody could comment, correct me if I'm wrong or right, but now we're just doing U2, V2, U3, V3. In other words, you don't have U3 here. You don't have, this isn't node 3, this is node 2, this is node 3. Now I'm pretty sure that's the case in almost, I think, every problem. I can't remember correctly, but that's pretty much the case in every problem. Just be consistent. Always put the lower node here, just to be safe. Again, unless one of you guys could correct me, because I'm gonna be honest, it's been a while. U3 and V3, okay? Let's go ahead and do that. All right, so C squared, S squared, C squared, S squared. Here they are both positives, 1, 1, so that's gonna be positive 1, positive 1, positive 1, positive 1. Then we got CS, negative CS, CS. So we got negative 1, positive 1, right? Because the signs switch them. And then negative 1. Negative C squared, negative S squared. So it's negative 1, negative 1. And then negative CS, which is a positive 1 now. Again, make sure you're using the right element, okay? Now we're doing element 2, so we use these numbers. And yeah, now we just, it's symmetrical, so we just move them down. So it's -1, -1, 1, 1, -1, and -1. All right, cool. That's it, right? It's just two beams, so two little matrices. Now we got to superimpose them together to make the global stiffness matrix. Now, we're going to have a 6x6, right? Because it's U1, V1, U2, V2, U3, V3. So we could go ahead and start doing that. Step 4. Let's go ahead and do the matrix, right? The huge equation. So it's going to be force 1x, force 1y, force 2x, force 2y. Let me move it up in case you can't see. And F3x, F3y. All right. So you got this. That's the vector for force. That's going to equal EA over 2L. So the reason we could combine them now, these matrices, is because they share the same stiffness value. This is dimensionless now in a way. Now this is the same stiffness. Okay, that's the reason we could combine these. If you saw 319, we had 3 elements, and one of these equations, one of these matrices, we had to alter in a way just so we could add them all at the end. But in this case, they have the same stiffness, EA over 2L. EA, L are all the same values. There's nothing different between them. Same properties, all good. So that means we could go ahead and add these matrices. So EA over 2L. Actually, you know what? Let's go ahead and plug in. So EA over 2L, EA over L was 70,170 divided by 2. You will get 35,355. And that's it. So now we could go ahead and start doing the matrix. This is going to be U1, V1, U2, V2, U3, V3. Same thing here. U1, let's give ourselves some space. V1, U2, V2, U3, V3. 1, 2, 3, 4, 5, 6. Yep. There you go. There we go. It looks right. And then the matrix, the vector for displacement. So it's U1, V1, U2, V2, U3, V3. Okay. So we're almost there. All right, so check this out. Before we start assembling this huge matrix, right, by adding each position using these matrices right here, let's go ahead and do the boundary conditions first to not waste time. So if you saw the other video, you know what I'm saying. But right here, this is node 1, right? This is node 3. So that means they're fixed. X and Y components, they're not going anywhere no matter how much force you put here. So U1 is 0, V1 is 0, U3 is 0, V3 is 0. So when you're 0, you just go ahead and cancel the rows and the columns. So U1 is 0, V1 is 0, okay, U3 is 0, and V3 is 0. Now same thing across, right? U1 is 0, these are a little bit longer, so let's go ahead and do this. Okay, V1 is also 0, U3 is 0, okay, I'm just canceling out the rows now, and V3 is 0. So all this is gone. So we don't have to worry about that. In this case, we're only concerned about 4 positions in this matrix. U2, 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 which is that one, U2, V2, which is that one, V2, U2, which is this one, V2, V2, which is that one, okay? So if you find those positions here, it's U2, V2, U2, V2. So U2, V2, U2, V2, we care about this one right here, we care about this one right here, this one, and this one. And on here, we care about U2, V2, U2, V2, so we care about this one, this one, this one, and this one, okay? So we could go ahead and add them. So 1, add both U2, U2s, 1 plus 1, that's 2. That goes here in U2, U2. Now U2, V2, so go to U2, V2 is this one, U2, V2 is that one, 1 plus -1, that is 0. And let's see, next one, V2, U2, it's -1 and 1, so that goes here. That is also 0. Finally, 1 plus 1 for V2, V2, that goes 2. So that's it. We didn't have to worry about anything else. Why? Because, again, these were fixed. This was equal to 0, this was equal to 0, this was equal to 0, and this was equal to 0. Those are boundary conditions. Now, we don't know the force of 1 at either x or y, and then same for 3, but we do know them at 2, right? So at 2, what is it? In the x direction, we have 0 force, okay? So it's 0, and in the y direction, we have a positive 10,000, okay? Positive 10,000, we'll go ahead and plug that in here. And now we could go ahead and just pretty much do the problem, okay? So let's go ahead and do that, step 5. And you could find force 1 at x and y, and then force 3 at x and y. And well, we're about to find U2 and V2, but you're gonna have 6 equations, 6 unknowns. And this problem is solvable, but I guess they just want displacement at node 2, okay? So let's go ahead and assemble the equation, right? For force 2x, it's 0 is equal to 35,000, don't forget that. 355. Now parentheses, 2 times U2, not U1, okay? You gotta know where you're at. 2 times U2 plus 0 times V2, which is just 0. Close parentheses. Next one, 10,000. That's equal to 0 times U2 plus 2 times V2. Oh, and don't forget the 35,000. Okay, so bring that down, and it was 2V2, okay? 2V2. And cool, just by solving this, right, step 6, U2, just by looking at it, is equal to 0. And then V2, if you do the math, 10,000 divided by 35,000 divided by 2, you will get 0.1414 inches. This is inches. And that's the answer. That's the displacement at node 2. All right. So now it's also asking, determine the stress in element 1. Now this is the equation. If you saw, I think 2 or 3 videos ago, I did 2 examples for stress. It's a C matrix. They call it C negative. I'm not sure why, but we'll just go ahead and call that times a displacement vector. Where that C matrix is equal to E over L times negative cosine, negative sine, cosine, and sine. Okay? That's the formula right there. We know E, we know L, we know cosine, right, of each element, and then displacement between what nodes is it in. So let's go ahead and write that down. Sigma of element 1 is equal to the properties of element 1. In this case, they're the same, okay? It's E, which is 10 to the 6, and then L, which is 141.42. That number is E divided by L. That number is going to give you, if you do the math right, 7071. Okay? That's E over L. Then open bracket, it's negative cosine for element 1, so it's negative radical 2 over 2. Okay? Then negative sine, negative radical 2 over 2. Again, you got to focus on element 1, okay? Element 1 right here. Then positive cosine, positive sine. So it's just radical 2 over 2, and then radical 2 over 2. And then displacement vector. So that displacement vector is between nodes 1 and 2, right? That's element 1. So you're going to use U1, V1, which is 0, right? 0, 0. Then U2, V2, because that's the other side of the node. U2 was 0, and V2 was 0.1414. So yeah, that's it. So now let's go ahead and just solve it, right? You should get one number. Well, why? It's because this matrix right here, it's a 1 by 4, right? 1 row, 4 columns. And this vector right here is a 4 by 1. It's 4 rows, 1 column. So you should get the force cancel out. The numbers should be equal to each other in order for this to work, 4 and 4. So that means you're going to end up with a 1 by 1, which is just one number. So sigma 1 is equal to, let me baby you guys, don't trip. So it's 7071. It's going to be negative radical 2 over 2 times 0, which is 0, plus negative radical 2 over 2 times the next 0, which is 0, plus radical 2 over 2 times a third 0, which is 0, plus radical 2 over 2 times 0.1414. That will give you a nice little 0.1. So that's it, 0.1 times this number, sigma 1. We're going to move it up in case you can't see. You should be able to see. Sigma 1 is equal to 707. Just move the decimal over one place. 0.1. This is in pound per inch squared. And that's the answer. So this formula you should know, right? Sigma is equal to C minus times D, where C minus is equal to all this. What else? You should know how to apply the boundary conditions, because you're going to waste a lot of time filling in these values. I mean, technically you're going to get the right answer if you fill them in, just that it's unnecessary work. We only care about these numbers at the end. Now, I mean, that doesn't mean we don't need them. So if you ever want to find force 1x, force 1y, force 3x, force 3y, then yeah, you got to fill in all these little numbers right here, every single number, because you need to assemble your equations, right? 6 equations, 6 unknowns. Use this table, trust me, it's going to help you. Start off with the element, the angle with respect to the x-axis, cosine of that angle, sine of that angle, square that, square this, CS, and then EA over L for each one. And that's pretty much it. There's nothing else that I really want to cover. Remember, this is for 2D problems, so you will always use this stiffness matrix. I don't even know what, yeah, it's a stiffness matrix for these kinds of problems. And I think that's pretty much it. Yeah, we should be good.